Hello, and welcome to the rear end collision. We've been talking about what happens when you get in an accident, because that understanding what happens in an accident, understanding all the forces involved, is a really good way to learn about Newton's first and second laws. Now we're going to talk about a specific kind of collision, okay? The rear end collision. So we talked about what happens if you're driving a car and you crash into something. But what if you're just sitting there and someone crashes into you from behind? Is that the same? Is your body going to do anything differently? The objectives for today, after this lesson, we will be able to evaluate from simulated collisions the effect of rear end collisions on the neck muscles. We will be able to explain the causes of whiplash injuries and the role of safety devices in preventing whiplash injury. And we'll be able to explain Newton's second law of motion. Let's talk about whiplash. I'm sure you've heard about whiplash before. Whiplash is a serious injury caused by a rear end collision. It is the focus of many lawsuits, loss of ability to work, and discomfort. But that doesn't really say what it is. It's a serious injury, but what is it? Look at the picture. What do you see? What is happening in this picture? What do you see in this picture? Take a minute, look at it, and then I want you to answer the questions. What is whiplash specifically? And then why is it more prominent in rear end collisions? Why do people get whiplash when someone hits them from behind? Alright, so these are some of my toys that I've been playing with while I'm on quarantine. And what I've done here is I've stacked up some books and I put a little ramp right here. And let's see what happens if I roll my little giraffe car down the ramp and hit my little Ford GT over here. Okay, just to take a little closer look, this is, obviously, this is a scale replica of a Ford GT40 MK2. It has a 3.5-liter twin turbocharged V6 EcoBoost engine and a 19-inch forged line wheels. Oh, 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 oh. And then this is my Ken Miles action figure. It was modeled after, of course, the British race car driver Ken Miles. And its lifelike detail comes from 2 blocks of wood connected with some tape, as you can see. And so the head here just kind of hinges back and forth. And so what would happen if I took my giraffe car and I put it up here kind of low on the ramp and I lined it up so that it's going to hit the Ford GT, and I hold my breath and I let it go? What's going to happen? Well, let's see. Oh, there it goes. Boom. It's going, it's slowing down, and finally the Ford GT comes to a rest. How far did it go? It went about 70 centimeters, right? What happened to the head and the torso of the action figure? Okay, the giraffe car came down, hit the Ford GT, what happened to the head and the torso of the wooden figure? Alright, I just had a really cool idea. What if I put the giraffe car all the way at the top of the ramp? Oh, okay. This is going to be crazy. So, I let it go. It's going, it's going. Boom! Oh no! Oh no. Oh, poor Ken Miles. Oh, I guess he got ahead of himself. So what was different about that run from the first run? Well, his head fell off, right? His head went flying off. I want you to tell me, what does that have to do with Newton's first law? Remember, Newton's first law is an object in motion will stay in motion. And an object at rest will stay at rest unless acted upon by an outside force. So how does that explain what happened to poor Ken Miles just right now? Now, this tape that was attaching the head to the body, how is that, what does that represent in a real human body? Do we have tape holding our head onto our body? No, of course not. What do we have holding our head onto our body? Well, it's the muscles and the bones in our neck, right? Those things hold our head onto our body. And is there anything that we can learn here? Well, we don't care very much about wooden heads falling off of wooden bodies connected by tape. We don't care about that a whole lot. But even though these are just little toys, there's still a lot of the same forces at work here that are at work in a real accident with real people, right? So this is something that scientists do a lot. If they want to understand something, they will create a model of it. And a model is just kind of like they set up a little small simulation. And they set it up so that things happen the same way they would happen on a large scale in a real situation. And then they study it, and they collect data, and they try to learn from it. So maybe by studying this little crash between toys, maybe we can figure out some things about real collisions. Maybe we can figure out how large a force must the neck muscles exert to keep our head from separating from our body during a rear collision. How much force are those neck muscles pulling on our head, keeping it on the body? Well, we're not going to cause any car accidents to get the data to answer this question. Okay. But by looking at the model, we can come up with an estimate. And this is what I was talking about. One thing that scientists figured out many years ago is that we can figure out small things if we have data about big things that work the same way. And we can figure out big things if we have data about small things that work the same way. And what we need to do is we need to use ratios. And ratios sound scary, but they're actually pretty darn easy. So, for instance, suppose you wanted to know how tall a very tall tree was, but it was quite a bit taller than you. How would you measure how tall this tree is? Well, of course, you could get a very tall ladder and a very long measuring tape and, climb up the ladder and drop the measuring tape down from the top and then, I don't know, read it somehow. I don't know how you'd get down there and read it before it fell over. That would actually be very difficult now that I think about it. So maybe it would be easier to train a squirrel to run to the top of a tree with a string around its tail and then measure the string later. Of course, you could always just cut the tree down and measure it, but then the tree wouldn't be standing anymore. There is an easier way, my friends. Use ratios. Ratios are math. No ladders or squirrels or chainsaws necessary. We can't measure the height of the tree directly, but we can measure its shadow. How does that help us if we can measure its shadow? We don't care how big the shadow is, we care about how big the tree is. Is the shadow always the same size as the tree? No. But doesn't the height of the tree affect the length of the shadow? If the tree is taller, the shadow is longer, right? If the tree is shorter, then the shadow is shorter. Now, of course, shadows also change with the time of day, but we're just kind of assuming that we're measuring shadows at one particular time. Okay, let's say exactly 4 p.m. We're going to measure all these shadows at exactly 4 p.m. If the sun moves, then of course the shadows will change, but that's not part of it. We're just looking at the shadows at exactly 4 p.m. All right, so we measure the shadow. We find out that it is 30 meters. Does that mean that the tree is 30 meters tall? No. No, the tree is not 30 meters tall because the tree and the shadow are not the same size. They're related, but they're not the same. So how can we figure out the relationship between the height of something and its shadow, since we can't measure the tree directly? Well, we could measure the height of something compared to its shadow. We just got to find something that's easy to measure down on the ground. How about that large rock over there? Let's use our tape measure and see how tall it is and how long of a shadow it casts. So we use our tape measure and we find out that this rock is 20 centimeters tall and its shadow is about 24 centimeters long. So what is the mathematical relationship between an object's height and its shadow's length? What is the mathematical relationship? Well, it all comes down to, mathematically, what is the relationship between 20 centimeters and 24 centimeters? What do I mean when I say, what is the relationship between those two things? Well, I mean, if you divide one by the other, how much bigger is one number than the other? That's what a ratio is. A ratio is a relationship between two numbers. It's a comparison between two numbers. So, 8 is twice as big as 4, right? 8 is twice as big as 4. So the ratio of 8 to 4, the ratio is actually 2 to 1. And if we had 8 over 4, we know that that would reduce to 2 over 1. And so this is the mathematical way to show that 8 is twice as big as 4. It's common sense. 8 is twice as big as 4. But this is the ratio that proves it. 8 is twice as big as 4. And that can also be expressed as a decimal. Okay, this is saying the same thing. If you say the ratio is 2.0, that's just another way of saying that 8 is twice as big as 4. The ratio is 2, or the ratio is 2 to 1. That's all it is. It's just division. So what if I asked you for the ratio of 12 to 4? Well, 12 to 4 reduces to 3 to 1, and obviously 12 is 3 times bigger than 4. So this is the way to say that 12 is 3 times bigger than 4. The ratio is 3 to 1. And remember that you can also express that as a decimal. If you say the ratio is 3.0, it's the same thing as saying the ratio is 3 to 1. What about 13 and 5? What is their ratio? Well, does 13 and 5, or sorry, what does 13 fifths, let's use math language here, does 13 fifths reduce to anything? Well, it doesn't, does it? It doesn't reduce to anything pretty. And so when numbers don't really divide into each other nicely like that, it's best to express the ratio as a decimal. So 13 fifths, if you put that in a calculator, it's 2.6. And so 13 is 2.6 times bigger than 5. I hope you see that. So now that you can determine the ratio between any two numbers, you know it's just division. What is the ratio between 20, the height of our rock in centimeters, and 24, the length of its shadow in centimeters? What is the ratio of the height of the rock to the length of its shadow? Well, congratulations if you figured out that you need to divide 20 by 24. Now be careful you don't put 24 over 20. Okay, you could get these switched, and you don't want to do that. I mean, you could do that. There's nothing wrong with that. If you say that the relationship between 20 and 24, if you just switch them, that's fine, but you have to do it that way always. You always put the length of the shadow on top and the height of the object on the bottom. You're going to get a different number, right? Because 20 divided by 24 is going to be a different number than 24 divided by 20. So just make sure that you're consistent. Today, we're always going to put the height of the object on top and the length of the shadow on bottom. And when you put 20 on top and 24 on the bottom, you put that in the calculator, you get 0.83. So that means that 20 is smaller than 24, right? So it makes sense that this is smaller than 1. So 20 is 0.83 times as big as 24. Now, here's where the cool stuff happens. We measured the height of the rock, we measured the length of the shadow, and we got a ratio. The ratio, 0.83. And we know that this same relationship between the height of something and the length of its shadow, that's going to be the same for everything that has a shadow. Everything's height is going to be 0.83 times its shadow length, because that's just how shadows work. At least until the sun moves, right? Don't forget that we're just looking at one particular time. 4 p.m. exactly. So now, using ratios, how tall is this tree if its shadow is 30 meters. Well, first of all, use your brain a little bit. We already said that the tree is going to be a little bit shorter than the shadow, right? So the tree is going to be a little bit shorter than the shadow. So when you get your answer, just make sure that that matches up with what you already know. So 30 meter shadow times 0.83 ratio equals 24.9 meters. So the tree is about 25 meters tall. No squirrels were harmed in this calculation. So, to summarize, when you divide one number by another number, you get their ratio. And if the same thing is happening in two different cases, but one is big and the other is small, you can measure the one that's most convenient and use ratios to figure out the one that's difficult to measure. Scientists do this all the time. We can't go into outer space and make measurements. So we find something that works the same way as things in outer space, and we measure that. And then we use ratios to multiply it up. And that's how we calculate things like the temperature in the middle of the sun. No one has gone there with a thermometer. We know how heat works on a small scale, and we can do calculations to figure out how it works on a big scale. And it's the same way with very small things that we can't measure. Things that are happening like inside atoms. We take other things that work the same way, bigger things that we can measure easily, and then we use ratios to figure out what's actually happening at a very small scale. So this is very important. Okay, if you're watching this at home, you should probably pause it, take a break, come back. Give your brain a little break. Alright, welcome back. So, what does ratios have to do with our question, how large of a force must the neck muscles exert to keep our head on during a rear collision? How can we use ratios to do that? Do you think we can use ratios to compare a small crash with my toys to a larger real car crash? Well, let's try it. Alright, so talking about force, we want to know how much force the head is, remember, the head is pulling on the neck muscles. The neck muscles are pulling on the head. They're both pulling on each other, right? So how much force does it take to move a real human head? Well, let's start with how much force does it take to move our small little wooden model head. We can measure force using something called a spring scale, which measures force in newtons. Let's try and figure out how much force it takes to move our action figure's wooden head over a distance of 30 centimeters. Okay, we got 30 centimeters here. The head weighs 0.2 kilograms. That's going to be important later. And also, we should go ahead and record the time it takes to move the head 30 centimeters. So the time it takes to move it from here to here. And instead of moving it randomly and then trying to time it, I think it would be better if I practiced how hard do I need to pull with the spring scale to get this block to move across here let's say, first of all, let's just do it for 5 seconds. Okay, we want the block to go from here to here in 5 seconds. And so I'm going to practice pulling it across until I know exactly how hard and how fast I have to pull it for this to be a 5-second trip. And then once I feel like I've got it down, I'm going to go ahead and do it. Okay, are you ready? All right, here we go. And go. I pull it, but it doesn't move at first. Okay? Because it requires a certain amount of force before it begins to move. So I'm pulling it. It hasn't started to move yet. This shows how much force is being applied to this block, right? It's a pulling force. This is how much pulling force there is. You can see it changed from here to here. Okay, now it's moving. So here's after 1 second of movement. Here's after 2 seconds of movement. Here's after 3 seconds of movement. Here's after 4 seconds of movement. Here's after 5 seconds of movement. So, how much force did it take to move this block 30 centimeters in 5 seconds? Well, it looks like about, if this is 0 newtons and this is 1 newton and this is 2 newtons and 3 and 4 newtons, it looks like it took about half, okay, 0.5 of a newton to get this thing to go. So the force on the spring scale read 0.5 newtons. All the way across, it looked like, right? So it takes about 0.5 newtons to move this head 30 centimeters over 5 seconds. I already said that. The surface is pretty smooth, so we're not going to worry about friction. Of course there is friction, but we're just not going to worry about that right now, because it's not convenient. All right. What if I pull hard enough? Okay, remember I practiced trying to get that thing to go, for this to be a 5-second trip. What if I pull harder and faster? I mean, I can't really control how hard I pull, but I can pull faster. What if I pull fast enough to move this 0.2 kilogram head 30 centimeters in 2 seconds this time? Do you think the force will be different? Why? Alright, well, let's see if you're right. And here we go. I got to pull it fast to get it across there in 2 seconds. Here we go. I pull it, and there it goes. 2 seconds. You want to see that again? Alright, here we go. And I start pulling. Here's how much force I'm pulling with. And then it starts to move. And there we go. It took 2 seconds. Alright, so how much force did it take to move that block 30 centimeters in 2 seconds? Well, hopefully you saw that it took about 1.3 newtons to move the block 30 centimeters in 2 seconds. So the force was bigger, wasn't it? Does that surprise you? Well, it shouldn't. Remember, we're saying that, you know, if you want to move the block 30 centimeters in 5 seconds, and then you want to move the block the same distance in 2 seconds, that's going to require more acceleration, isn't it? And you know from F equals ma, or A equals F divided by m, you know that if there's more acceleration, then there has to either be more force or a smaller mass. And we didn't change the mass, it was the same block. And so if we wanted a bigger acceleration, we needed to have a bigger force. What if I pull hard enough to move the 0.2 kilogram head 30 centimeters in 1 second? Do you think the force will be different? Well, hopefully you said yes. Let's see if you're right. Alright, I'm going to have to pull it really fast this time. You ready? And go! I pull it. And there you go. Moved it all the way across there in 1 second. That went pretty fast. You want to see that again? Alright, here I go. 3, 2, 1. Oh, I pull it. And there it goes. How much force did it take to accelerate that object 30 centimeters in 1 second? Well, hopefully you see that it's about 2.5 newtons. So now, knowing this, what would you say is the relationship between the force that is applied to an object and the time that it takes to move across a certain distance? The shorter the time, the blank the force required. The shorter the time, the blank the force required. Well, the shorter the time means the greater the acceleration, right? So the shorter the time, it should be the greater the force needed. The shorter the time, the greater the force needed. Alright, we know the mass of the wooden head. And we pulled on the wooden head with 3 different forces and saw 3 different accelerations. 3 different forces. Now, one thing that would be really helpful, because remember, we're comparing the small crash to a big human-sized crash, a real crash with real people. And we're comparing this tiny little wooden head to a real human head. So it would be helpful to have kind of an estimate of what the mass of a normal human head is. Do you know the mass of a normal human head? I don't. The only way I know how to do that is to go into my bathroom and put my head on the scale. But that's not very reliable because, you know, your neck is still pressing down and stuff like that. So, in my book that I have, it points out that since the body is mostly water, you can assume that the body's density is very similar to water. So there's going to be a lot of times in science where we just kind of treat the body like a big bag of water. And that's okay to do because we really are mostly water. Not totally, but mostly. And the things that aren't water, they have a different density of water, but not a super different density than water. Okay? So, if I want to know how much an average human head weighs, if I want to know how much my head weighs approximately, I can just put a bag over my head, get the shape of my head, the size of my head, then take the bag off and fill it with water. And I did that. And I weighed it, and it was 14 pounds. It was 6.4 kilograms. So now we have the mass of a small wooden head. We have an estimate of the mass of a human head. And we have data about accelerating the wood head with 3 different forces. 0.5 newtons, 1.5 newtons, and 2.5 newtons. I think we have enough information to calculate how much force our neck muscles have to use to keep our head on during a collision. Let's try it. All we should have to do is find the ratio between the mass of our real head to the mass of our wood head. Okay, one is obviously bigger than the other. How much bigger is it? And then we can take that ratio and we can compare the forces that we applied to our wood head, right? And we can just multiply that by the ratio, and that'll give us the force on a real human head without us having to experiment on a real human head. So let's try it. Let's find out what the ratio is of the real head to the wood head. Well, remember, the real head is 6.4 kilograms and the wooden head is 0.2 kilograms. So what is their ratio? Their ratio is 32, or 32 to 1. 32 over 1, if you wanted to write it as a fraction. So a real human head is about 32 times more massive than our little wooden head that we're using. So now that we have the ratio, okay, we're going to apply that ratio to the force on a real head compared to the force that we had on our little wooden head. So 32 equals, we got to find out what are these values. So what is this value going to be? Force on real head. Well, we don't know what that's going to be. That's what we're looking for. What about this one? Force on wood head. Well, we have 3 of them, right? What was the first one? First one was 0.5 newtons. So plug in 0.5 newtons here on the bottom. And you get 32 equals x over 0.5. Actually, instead of x, we should call it F, right? Because we're looking for force. So 32 equals F over 0.5. If you do some algebra to that, if you do some algebra to this, we're looking for force, so we should get F all by itself. And if you want to do algebra, you just multiply both sides by 0.5, and you get F equals 0.5 times 32, and that is 16. And it's force, so of course the units is newtons. So what would the force be on a human head if we accelerated it the same as the wooden head when we applied it 1.5 newtons? So instead of 0.5 newtons here, what is the equivalent for 1.5 newtons? Force equals okay, now this is force and this is force. This is the force on the human head, and this is the force on the wooden head. Do you see that? So force on the human head equals the force on the wooden head times 32, because we said that the force on the human head is going to be 32 times bigger. So 1.5 times 32 means that if we accelerated it the same as when we applied 1.5 newtons to the small wooden head, if we accelerated it the same, then the force on the human head would be 48 newtons. How much force would be on the neck muscles trying to hold that head on? Well, that would be 48 newtons too, right? If the head is pulling away with 48 newtons, then that means that the neck muscles are pulling on the head with 48 newtons. And in the third one, when we applied 2.5 newtons to the small wooden head, that's the same kind of thing. Okay, that's simulating 80 newtons on a real human head. That's a lot of newtons. That is a lot of newtons. Now, one other thing I want you to see here is that because the ratio is the same from real head to wood head, and it's the same for real head to wood head and the ratio of the masses is the same and the ratio of the forces is the same. And so since they both equal 32, we don't even need to bother with saying that it equals 32. We know that they are equal to each other. The mass of the real head compared to the mass of the wood head is going to be the same as the force on the real head compared to the force on the wood head. Now, does that mean that the mass of the real head is going to be the exact same number as the force on the real head? No. These numbers are going to be different, or they can be different. And these numbers can be totally different. The only reason they're the same is because after you do the division, that number is going to be the same after you do the division. And hopefully this looks familiar to you. This is where you could start doing some cross multiplication if you wanted to. That would be fine. All right, whiplash is a serious injury that can be caused by a rear-end collision. The back of the car seat pushes forward on the torso of the driver and the passengers, and their bodies lunge forward. Okay, just their bodies lunge forward. The head, because the head is not pushed by the seat, the head remains still. It doesn't get pushed. And the body moves forward, and the head remains there, and it actually causes the head to snap backwards because the body and the car are moving forward without the head. And then the neck muscles and the bones of the vertebral column become damaged. The same muscles must then snap the head back to its place atop the shoulders. And if you remember that cartoon at the very beginning, that woman, that poor woman, her head was going backwards really fast, but it was also going forwards really fast. Okay, once your head snaps back and those neck muscles pull on it, they stretch, but then they pull, and that pulls your head forward. It's like it's on a spring, kind of. So your poor head and your poor neck get damaged on the way back, and they get damaged on the way forward. And I found this video that's actually pretty good. It even talks about Newton's laws, which is surprising because this guy is not a scientist. He's a lawyer. So let's take a quick look at this.
Your business idea needs a website? So go to Wix.com. What are you waiting for? Today's the day.
It's like playing by Braille.
Sir Isaac Newton described the laws of motion in 1687. The first law of motion basically says an object at rest will remain at rest until it is acted upon by an outside force. And an object in motion will continue in motion with the same speed and direction unless acted upon by another force, which is called the law of inertia. In simpler terms, this means that there's a natural tendency of objects to keep on doing what they're doing. All objects resist change in their state of motion. Sir Isaac Newton's second law of motion basically says acceleration is produced when a force acts on a mass, and the greater the mass of the object being accelerated, the greater amount of force it will take to move it. With these two general explanations of the laws of physics, let me show you what happens in a simple rear-end car crash. Before the moment of impact, the person inside the car and the car itself are resting without motion. As soon as the car is hit from behind, the mass and energy from the moving car begins to transfer energy into the stopped car. What most people don't understand is that the body of the person sitting in the stopped car will not move immediately with or as quickly as the car they're sitting in. But instead, there is a lag in time before their body starts to move. In this graph, we have time going along the bottom and g-forces are on the left. The steel frame of the car being hit will begin to accelerate forward from the impact. However, the person in the car will resist moving due to Newton's law of inertia. What will happen is the vehicle will begin to move before the occupant. The vehicle may actually move several inches forward while the person's torso begins to increase pressure against the back of their car seat. Note in this picture how the driver's hand is off the steering wheel. Then, the pressure from the seat shoots the torso of the human body forward like a diving board propels a diver. The torso moves first, and because your head is somewhat like a bowling ball supported only by your neck, your head will remain motionless for a few more milliseconds. So the car moves first, then your torso moves out from underneath your head. This forces your head to suddenly have to accelerate to catch up with the car and your torso. This very sudden acceleration of your head causes 2 points of stress in your neck. The first stress point is at the cervical vertebrae C5 and C6, and the other stress point is between the cervical vertebrae C1 and C2. These two areas of our neck usually get the most damaging forces, which oftentimes tears or permanently stretches the ligaments that hold our vertebrae in their proper place. It is these exact same laws of physics that cause mild traumatic brain injury.
All right, we don't care about brain injury that much. At least that's not what we're talking about in this part of science. So I want you to think right now and answer the question, what types of safety devices can reduce the delay between body and head movement to help prevent injury? And these could be safety devices that most cars have, or they could be experimental safety devices that aren't common yet. So what types of safety devices can reduce the delay between body and head movement, or do reduce the delay between body and head movement to prevent injury? Well, the one I think of is headrests. You know, the headrest on the back of your seat. The whole point of that is to prevent your head from going too far back. And if it doesn't go too far back, then it's probably not going to like whip forward as badly. And what else? What other safety features have been added to cars to help reduce the number of injuries resulting from rear-end collisions and the severity of injuries resulting from rear-end collisions? What do we have on our cars that prevent rear-end collisions and reduce the injury in rear-end collisions? Well, the ones I think of are rear bumpers. Okay, hopefully someone will hit your bumper. And bumpers are designed to absorb some of that energy from the collision. And as that bumper gives way, it pushes the car forward more slowly and absorbs some of that energy. Also, cars are designed with weak points so that they will actually crumple up like smashing a tin can. And this also absorbs lots of energy. Cars are also equipped with brake lights. You know, why do cars have brake lights? You can't see your own brake lights. So why do they have them? Well, it's for the people behind you so that they know that you are stepping on the brakes, which means you're going to be slowing down. Kind of gives them a heads up.